So on the previous page, it seemed like I pulled off a little bit of a magic trick because I knew, since this was a 45-degree angle, what the length of that vector was going to be. But of course, that's not going to work all the time. We need a method that's going to work for finding the magnitude of a vector. And that would be right here. So the magnitude is the length of that vector. And that is calculated as such. And it is very much related to the absolute value magnitudes that you learn about in algebra class. That's why it has the vertical lines around it. Because, of course, when you're working with one-dimensional stuff like you are in algebra class, the magnitude is the same thing as the absolute value. But, of course, because we're working with more than one dimension, it will be more complicated. We're not just working with a number line. We're working with an x and a y axis and later a z axis as well. And of course, this is happening because of the Pythagorean theorem. If you think of the way a vector works, if you have, A over here and B over here, then the length of the vector itself, which is from that point to that point, would be the square root of A squared plus B squared, right? It's the Pythagorean theorem. All right, so let's use this as an application to do some examples. We're going to find the magnitude of vector C. So the magnitude of C, so we put little absolute value symbols around it. And I will tell you, sometimes they will do double absolute value symbols around it, depending on the book. I believe some computer programs use the double absolute values as well. So just be warned. It's the square root of, now you have to be careful because A is all of -3. And you're going to square it, which is going to turn it positive. You don't want to leave the -3 outside of the parentheses, right? You want to square it. So that would be the square root of 9 plus 25, which is the square root of 34. And that's it, right? It's the square root of 34. There are no perfect squares that go into that, so there's nothing to reduce. All right, so now let's look at PQ as the vector from -4, 2 to 6, -6. How would we find the magnitude of that? Well, it would help if you could find A and B. And you might notice from over here, we actually learn this formula when you're learning it in geometry class. You learn it as a distance formula. That's the same way it works. So let's just make some notes here. So PQ would be, okay, so this is initial because it's from this to this. This is the terminal. So terminal minus initial. So 6 take away -4. And then -6 take away 2. So that would be 10 and -8. And then if you want the magnitude of PQ, you would take the square root of this. So I'm going to write it this way just so you guys can see. Because the note is actually getting at something here. And that would be the square root of 164. Now that reduces. There is definitely a perfect square that goes into 164. And of course, I could use something easy like Desmos to find this, but I figured why not show you in Maple. So in Maple, I'm going to produce a new document, and I'm just going to hit enter a few times so that I don't have to. Sometimes you can run out of spaces. I'm going to hit square root 164. Sorry, it froze on me because it wants me to download some updates, which I'm not going to do right this second. And there we go. So it tells us it's 2 square root of 41. Sorry, that's probably super small. There you go. Now you can see it. So it's 2 square root of 41. Simple as that. So it's over here in the palette. You can also type SQRT if I'm not mistaken. Yes, 164. And there you can see it's 2 square root of 41. There we go. Okay, so this would reduce to 2 square root of 41. Now, what we were getting at with this geometry formula is when you look at it like this, that should look familiar to you because that's the distance formula that you learn in geometry class and algebra 1 class, the distance between 2 points, right? because that's what you're finding, of course. It's just that there's got a little more oomph to it now because it's a little bit more than just the distance. It's direction and magnitude, right? So what you're really seeing is the magnitude. And the distance is just a visual way to represent that. All right, so now let's look at vector A right here. Okay, so we kind of have to figure out where these points are. So the initial is 1, -2. And those are in parentheses because they're points, right? This is a point, not a vector, right? The bracket notation is a vector when you have the kind of jagged sides to it, like up here. That's a vector. All right, now the terminal is right there. So it's over 5 up 4. Great. So now we can use that to find vector A. So vector A would be the terminal minus the initial. You just never want to forget that. Okay, so see, vector. So terminal would be 5, take away initial, which is 1. 4, take away -2. So that's 4, 6. So that's vector A. That wasn't what was asked for, but we needed to find it in order to be able to find the magnitude. Now the magnitude of A, which is the length of that, would be the distance between the terminal and initial point. So that's the square root of 4 squared plus 6 squared, which is the square root of 16 plus 36. So that's the square root of 52, which again reduces down. I can show you in Maple. I'm just going to do it right here. The square root of 52 is 2 square root of 13. Right there. Sorry, I went back to the screen and I've got to make Maple go away. There it is. All right, so now let's take what we're learning and let's do some vector arithmetic. Right? So the scalar multiple of a vector. So if you take a vector and you multiply it by a scalar, then you're just multiplying every component by that scalar. It's very simple. So for example, if I have vector v, which is -2, 1, right? So over -2 up 1. So I'm going to draw it in standard position right there. So there's vector v. All right, I want to find 2v and -3v both graphically and algebraically. All right, so let's find 2v. I'm going to do that with green here. 2v would take the vector and multiply it, so the vector -2, 1, and multiply every component by 2. So that would be -4, 2. It's the same direction as v, but it's twice as long because it's going to go out to -4, 2. So it's going to be like that. So this is the same direction as v, but twice as long. Sorry, that got off the screen there. All right, now let's look at -3v. Because -3 times that vector would make it go 6, -3. And that's not the same direction. 6, -3 would be over 6 down. So what direction is that? It's the opposite direction, right? So this is the opposite direction because we multiply it by a negative as v, and 3 times as long. Well, that seemed pretty straightforward. What about adding vectors? Well, adding vectors is also pretty straightforward. You just add the component pieces. So let me just highlight vector addition here so you can see that it's a definition. Okay, so we are going to take vector v, which is 3, 1, and vector w, which is 2, 4. And we're going to find v plus w both graphically and algebraically. Okay, so vector v, I'm going to do this way with red. So over 3, up 1. There's vector v. And vector w is 2, 4. And the way to do this graphically is to attach the 2, 4 onto the end and pretend this is the initial point of the vector. Because vectors are free, you can put it anywhere you like. So you're going to take this and you're going to go over 2, up 1, 2, 3, 4 from that point. So that's going to get you right there. So this is vector v right here. This is vector w right here. So can you see where this is going? Vector v plus w would add the two vectors together, and you'd start at the same initial point as v, and you'd end at the terminal point of w. So this is the vector v plus w. Now let me prove it with the formula. So v plus w would be 3 plus 2, and then 1 plus 4, which is 5, 5, which is indeed what I drew, right? This is over 5, up 5. It connects the two. And I want to do subtraction before I end this video because they're connected, right? The addition and subtraction, you can imagine. Okay, so with v, it's still 3, 1, right? So you still start at 3, 1, like that. But w, you want to subtract it. So instead of going positive 4, well, up 4 over 2, or over 2 up 4, because you're going to subtract it, it's going to become negative. Let me show you. So v take away w would be 3 take away 2 and 1 take away 4, right? So you're going to subtract. So they're both going to become negative. So for the x direction, I want to subtract 2. So I'm going to start here at the end of the terminal point of my first vector v. And I want to subtract 2. So I'm going to go to the left 2. I'm going to go down 1, 2, 3, 4. And it's going to get me right here. So that's negative w. And this is positive v. And then when I put them together, that gets me this vector, which is v take away w. From the initial point of v to the terminal point of negative w, which is 1, negative 3, which is exactly what I drew. It's over 1, down 3. So let's just make a note, because it's a little strange with these ones. It's v plus negative w. Right? That's what subtraction is. So it's v, if you will, plus negative 2, negative 4 for drawing. Right? Just kind of think of that.